Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, thanks for coming. We're welcoming Abhishek Kumar today from University of Maryland College Park, where he's working with Hal Demay on a number of interesting topics. And today he'll tell us about the work he did at IBM T.J. Watson with Vikas and Sindhwani on matrix factorization, which we all like and use.
Thanks, Misha. So I'll talk about algorithms for separable non-negative matrix factorization. And here is the outline of the talk. So I'll start with introducing the problem of NMF and the separability assumption. And then I'll talk about algorithms for near-separable NMF. In the next part, I'll talk about extensions of these algorithms to other loss functions like L1 loss or Bregman divergence. And in the end, I'll talk about some other work that I've done. So let me start with introducing the problem of NMF. So the problem setting is that we are given a non-negative matrix X here, and the goal is to factor it into two matrices W and H, so that the product W times H is close to X in some distance measure. And again, W and H are also non-negative, so all the entries of these matrices are greater than 0 or 0. The small r here is the inner dimension of the factorization. It's always usually much less than both m and n. So non-negative rank is the smallest inner dimension for which we have an exact factorization. So there is no error in the factorization here. So the smallest r for which we have no error in the factorization, that's called non-negative rank. And important point about non-negative rank is that it's always greater than linear rank and always less than or equal to both m and n. Now another point about NMF is that it can be non-unique. So even if we ignore the permutations and scalings of columns of W and rows of H, NMF can still be non-unique. So there can be multiple non-negative matrix factorizations for a given matrix. Now let's understand the motivation behind NMF with a small example here. So I've shown the images from a database called Swimmer, and it has images of a creature that is swimming, and it has 4 legs. So 4 legs can be in 4 different orientations. So there are total 4 to the power 4 256 images, and each image is of size 32 cross 32. Now let's say we vectorize all these images and put them along the rows of a matrix X. So X is now 256 times 1024, and we do a low rank factorization on X. So we factor it as W times H. Now in this model, every row of X can be seen as a linear combinations of rows of H, and the combination coefficients are given by the corresponding row of W. The rows of H are called bases if they are linearly independent, and if they are not linearly independent, we call them topics or dictionary. Now suppose we have non-negative W here. So what does that mean? That means that we are combining the rows of H additively. So we are adding the topics to generate every data point. So it gives a very clear, nice interpretation to the model. On the other hand, if we don't have non-negativity on W and H, in that case we can get a low rank factorization using SVD as well, which is optimal in terms of minimizing the Frobenius norm between X and W times H. So let's see what basis we get using SVD here. So this is the basis we get using SVD, and again each basis image is a row of matrix H which I have reshaped to display as an image. So here you can see the topics are not very interpretable. Now as soon as we put non-negativity constraints on W and H, we get interpretability in topics. So you can see that every image in the database here can be generated by adding all these topics, and we also get sparsity in the representation because
your was Frobenius norm as well there. Your goal was to reproduce the matrix,
right? So
according to Frobenius norms.
Yeah. So
in case as well. Right?
Yeah. So the objective function is this: to minimize the Frobenius norm between X and WH.
Right.
So we also get sparsity in the representation because of non-negativity. So in this example, you can see that we can generate any image in the database by using at most 5 topics from this set of 17 topics. So we get a sparse W, and which is again useful in some applications. Now NMF has various applications, and one of them is topic modeling. In topic modeling, we are given a corpus of documents, and the goal is to learn prominent topics from this corpus. Now let's say we represent our corpus as a matrix X here, where each row is a document. So X is document by word matrix, and we factor it as W times H. So W is document by topic, and H is topic by word. So here every document is generated by additively combining the topics, the rows of matrix H. So here I have shown some topics that are recovered using NMF. So again each topic is a row of H, and you can see the first topic is corresponding to some Olympic Games, second topic corresponds to space mission, and third corresponds to stock market, I guess, and so on. So NMF does give us reasonable topics. Yes.
So you're probably going to answer this later, so feel free to just say it. So given H, which are your topics, and like some new document that wasn't in the document word matrix originally, it'd be nice maybe to say, hey, what topics is this new document in?
Right.
That means it's sort of like computing a little bit of W for this new one.
Exactly. Yeah.
But it's not part of the overall process because the topics are fixed at this point, let's say.
Yeah.
So what is, you're going to talk about that computation, because that computation is not necessarily simple in my mind.
That's true. So if the new, you know that the new document belongs to these topics, then that's
not as much as any of the other documents.
I mean if there is a novel topic there, then that's a problem.
Okay.
Otherwise,
let's assume it's from the same distribution of size.
Yeah, if it is from the same distribution, then you can basically solve a problem which minimizes the distance between X and W times H. Where you know H and you know the vector X, and you solve for W.
But you also, once again, you need non-negative W.
So you solve a non-negative least squares problem with unknown W. Yeah.
And is that fast? I mean, in a weird way, it's kind of like you can spend all the time in the world finding some topics, but then maybe I'm going to have 20 billion documents.
Yeah.
So I don't really want to spend all that much time per document figuring out what topics this document is about.
Yeah, I mean, in my experience, it's definitely faster than latent Dirichlet allocation if you have NMF, and that's faster than LDA. But yes, again, I mean, you have to parallelize and do all sorts of optimizations to make it work. So other applications of NMF are in hyperspectral unmixing, blind source separation, and also in a few unsupervised feature extraction problems in computer vision. So it was shown in 2009 that, yes?
I'm sorry, I'm missing some intuition. So why does NMF give you that more sort of topic-oriented inseparable thing than SVD?
Here?
Because you just not being able to go negative forces it somehow, like what's the intuition there?
So intuition here is that when you have non-negativity, you are only allowed to add the topics.
Right.
So every topic in some sense is forced to pick certain parts of the images from the database.
Okay, whereas SVD, they can trade each other off.
Yeah, and SVD you also have negativity, so you can basically trade off. Okay. And now because you are forced to pick certain parts of the images, so you'll pick those parts which are appearing in most of the images. So that's why you get the topics here.
So for a given number, for a given R, will the SVD will give you a better fit to your X, but the NMF will give you this more interpretable fit, I guess.
Yes, that's true.
So is it so there might be multiple ways to do that, right? You could do L1 regularization, you could do this kind of positiveness constraints. So what is the drive there to use this strategy as opposed to, let's say, L1 or projection onto some sphere or something?
So L1, with L1 you will not get non-negativity. You can get like you can get several zeros, but you will have also negative elements. So I guess this type of interpretability you will not get even if you use L1 regularization on W and H.
And does it mean I have to pay a price compared to doing, for example, SVD with L1 regularizer?
SVD with L1?
Yeah, let's say I do this and I put an L1 regularizer because I'm not satisfied with those topics.
Right. I think SVD with L1 will be non-convex. So again, I mean this. So this SVD is also non-convex, but you can get a global solution because it's an eigenvalue problem. But if you put a L1 norm penalty in the objective, then I guess you will reach some local minima. So first problem is that it will not be a global optima, and second is I don't think you will get interpretability like you get with NMF. Yeah.
So you have the okay. Thank you.
Yeah. So in 2009, it was shown that the problem of NMF is NP hard, problem of exact NMF. So it also means that the approximate NMF problem is also NP hard. Now I'll mention a few problems that are solvable in polynomial time. So the first problem that can be solved in polynomial time is if we treat the inner dimension of the factorization as constant. In that case, the complexity is polynomial in n and m, but still it is exponential in R, so it's not very practical.
I guess I'm a little confused because why wouldn't it be a constant? Isn't R an input to this algorithm or something?
Yes, R is definitely an input.
I see.
But the complexity here is exponential in R, so it's exponential in the size of your data.
Right.
So it's NP hard. But if you treat R as a constant, then it's polynomial in n and m. So complexity is like n times m to the power r square 2 to the power r. So it's actually double exponential in R. Yeah.
There's a practical result.
So second instance when the problem is solvable in polynomial time is when rank of your matrix X is 1, or you are seeking a inner factorization of inner dimension 1. So in that case, if you do SVD on a data, you directly get NMF because top singular vectors of a non-negative matrix, they are non-negative. Third case is when your rank of data is 2. So in that case also it can be shown by some geometric arguments that NMF can be solved in polynomial time. Now because NMF is NP hard, the most common approaches to solve this problem are based on local search. So these approaches start by randomly initializing matrices W and H, and then they fix one block of variables and optimize for others. And this is repeated for a number of cycles until the approach converges to some stationary point. But the problem is that these approaches are not guaranteed to converge to a global optima. So that's the danger with the local search methods that can converge to different stationary points depending on the initialization. So separability assumption was proposed to make the otherwise NMF problem tractable. So the assumption basically says that you have an identity matrix that is hidden somewhere in your right factor matrix H. So in other words, some columns of H are coming from the matrix identity. So if you look at the matrix inside the bracket here, the first R columns are identity and the rest of the columns are given by H prime, and the columns of identity are hidden by this permutation matrix P. So and we don't know where they are hidden. So in other words, the assumption is also equivalent to saying that we have some columns of matrix X that make up matrix W. So the columns that are given by the index set A, those are the columns that constitute W exactly. Now those columns of X that appear in W, we call them anchor columns, and here I have denoted them by the index set A here. Yes.
Maybe possible, maybe isn't. Sometimes people use this notation for conjoining matrices. Sometimes it just makes sense for me to draw a picture where you're like, okay, see this little block of the matrix, that's the identity. Yeah. See that block over there, that's not the identity. These are zeros or something. Can you do that picture for us? Or are you about to do that picture?
Yeah, no, that picture is unfortunately not there.
There's a whiteboard and their
sure.
pens.
Okay. So the picture looks like this. Say you have this big matrix X,
sure,
which is equal to
right,
and then here you have some columns that are coming from identity. So maybe this column is from identity, and somewhere else you have some other column. But you don't know where these columns are appearing. So
okay.
yeah. and rest of the columns can be anything. They can be any non-negative values.
Now I'm just thinking about column
When you multiply W with the column of identity, that column transfers directly to X.
That row.
So wherever you have this 1 appearing, so the second column of W will be transferred to that position.
So you're saying a word can only belong to one topic, effectively?
You are saying that in every topic there is at least one word that is not appearing in other topics.
Another topic. So
So there is at least one
there are
unique
words
word.
which are uniquely belonging to a single topic.
Yes.
I see. And that's why the word anchor.
They are called anchor words, and it's kind of reasonable to assume in topic modeling. Because if you take like 2 topics like sports or politics, you can assume that there is one word in sport that is not appearing in politics, and so on.
Right.
But it's stronger here. So you're saying that H prime is orthogonal to those as well?
H prime is not orthogonal.
H prime is not constrained.
H prime can be anything. So they can be anything non-negative.
Okay.
Yeah.
Good. This is very helpful, by the way. So for your next talk, you should have it.
Yeah, that's a good suggestion.
At least it was helpful to me.
So the columns where we have identity, they are called anchor columns, and you can see that rest of the columns are just conic combinations of these anchor columns, because H is non-negative. So all the columns of X, they are generated by non-negative combinations of these anchor columns. Now the problem of NMF is reduced to finding the extreme rays of the data cone here, and the reason is that if you have these extreme rays, they are generated by the anchor columns of X, and once you have the anchor columns, you can get directly matrix W, and then you solve for H. So here is a geometric picture of the problem. So the points here are the columns of X, the matrix X, and red points are the anchor columns, and black points are rest of the columns. So in this picture, you can see that all the points, all the columns of X, they are inside the conical hull of the red points.
So can I just say one more thing? So the anchors, there's one condition on the anchors, which is, I'm just going to say intuitively, there's some words that are only in one topic. Right, that's one way to think about it.
Yeah.
But it's actually, you're relying on another property of this, which is in fact, you get the whole identity matrix. So that for every term, that term must occur in only one topic. There must be some topic for which it only doesn't occur. No, I'm wrong. So because you're saying it's in the linear combination.
Yeah, so assumption is that in every topic you have at least one word that is not present in others.
There are other words are just a combination of the anchor words. The words that are shared, they can be represented in the space of the anchor words. Is that?
That's also one way to say it.
In a weird way, these words are sort of like if you just knew these magic words,
then all the other words are just points in the space that is determined by the basis of these anchor words.
Yeah. Okay.
Now suppose we cut this cone by a positive hyperplane. So the hyperplane is given by P transpose X equal to C, and P and C both are positive. And then we scale all these points so that they lie on this hyperplane. So the problem now reduces to finding the vertices of the convex hull of the scaled points, because the points that were anchor columns earlier, they are now vertices of this convex hull. So we can also solve this NMF problem when we scale the data and then find the vertices of this convex hull of the scaled points. Now the question is it a reasonable assumption or not? And in topic modeling, it is a reasonable assumption, as we discussed, that there is at least one word in every topic that is not present in others. In hyperspectral unmixing also, it's a reasonable assumption, as it has been pointed out by some recent papers. And in general image processing, the answer might vary from application to application. In some of them, it might be reasonable, and in the end, I'll show one application where it does give good results. Now, so far we saw a pure separable problem. In the noisy problem, yes.
Yeah. But there could be exponentially many vertices. How does that scale?
So So for a real data set, yes, there can be many vertices, but you want to pick the vertices which will give you the least factorization error. So because you are restricting the rank of your factorization, so you want to pick only small r number of vertices. So you want to pick those vertices that will give you less factorization error.
You can view factoring a biprime as finding a vertex on a convex hull over a certain space in the region it's possible with zero exponential rate. So I'm wondering if you have a similar problem. There's a search problem for
Yeah.
vertex.
Yeah.
So how many vertices are there? How does it scale?
Yeah, I mean, so if you have n points at most, you can have n vertices. I mean, depending on the dimensionality of the space, that will vary. But it turns out that if you have to select so in every iteration you can select one vertex of the convex hull, and if you have to pick all the vertices, that problem can be solved in polynomial time. But again, you have to be selective in picking the vertices. So yes.
So again, I feel like I'm missing some intuition because it feels like we sort of added something very tiny and got too much gain for it. So, I mean, all we need is that there's at least, for each topic, there's at least one document that has one word that was the only time that word appeared. Like, this seems like a really trivial thing to add to your set, and all of a sudden it becomes not NP. Is that right? That's all you need.
It's kind of like a marker. It's almost like a cheat.
But you only need the word to appear once,
no,
like in one document?
No. So there is no notion of document in the matrix H. So H is topic by words. Right. So you assume that the topics that you are recovering, those topics have this property that.
Right. But I mean, in your X, that word only needs to appear in one of the rows, right? That topic.
But it has to have a huge weight to be in the solution. I mean, it has to have a huge weight. The solution has to be like that.
So, I mean, so the anchor words can appear in multiple documents, for example.
Right. But at a minimum, it only has to appear once.
Yes,
of
course.
If it only appears once, it won't be in this solution.
It needs to occur in every document that has that topic.
Yeah. No, but
So at least one of the anchor words for a topic has to appear. So there can be multiple anchor words for a topic, right?
For a topic, there can be more than one anchor words. That's true.
There can be, but we've assumed that there is at least. That's where that identity matrix thing comes from. The identity matrix is, it has one in every column and one in every row.
But like you
But
can
have
have
extra stuff.
But is it then true that the other words that are going across multiple topics, they have to occur with at least one of the anchor words for each topic for them to be discovered? Is that so? The words that are not exclusive, the words that are not anchor,
Right.
for them to correctly get identified as having some weight to the topic, they have to co-occur with at least some of the basis words.
of the anchor words.
Yeah, of the anchor words.
Is that true?
Mm-hmm.
So if I had only one document given all the documents on a topic, if only one of them had my anchor word, that won't work. It needs to, unless that document happened to have every other word of that topic also.
Let me see. So actually, so if you take a particular column of this matrix H, right? That column generates the corresponding words in the matrix X, right? And that column is responsible for combining the columns of W, right? So in your document, it is possible that the anchor word is not present. That's possible, but so you have these columns of W that are getting combined, right? And the combination coefficients are yes, I think you are right. So if the topic is present in a document, then anchor word has to be there. Yeah.
You can kind of I think you can sort of look at that diagram and just label M and N. I mean, one of the problems with using M and N is that it sort of sounds like it's just numbers, but it's not, right? I mean, M is documents, N is words.
M is the number of documents.
And then N is words. And so then you can now label W and H. So W has documents vertically and topics horizontally.
Right.
And then H has words
By topic.
by topic.
Right.
And so now you look at it, and it basically any document that has topic 5 or something like that
Has to have that word.
has to have that word. That's the definition of it.
Yeah.
That's what that inner product means.
So every row of H is a topic, and yes.
It's like if you only knew what that word is, then you could just read off the answer. That's what makes it sort of extreme.
Within the approximation.
I think what's hard is that you give this simple condition on the solution, but it's hard to figure out the space of document matrices which like have this property, right? That, well, I get some data. Does it have this anchor property? Maybe you come up with a simple test or something.
Yeah, I mean, so there is no test, but it has to come from the domain knowledge that you have. So for topic modeling, I mean, it's a safe assumption to have that if your topics are discriminatory, then you can say that you can assume that there will be at least one word that discriminates it from other topics. But if you have very close by topics like in sports, if you have like baseball in West Coast and baseball in East Coast, then maybe they are not very discriminative. So in that case, maybe all the words are common between these two topics.
And is your algorithm finding the best solution, assuming that, or is that if I give it an X matrix which might not verify that, would fail, or?
Yes, so it's a global solution under that structure.
Okay. But if I give a matrix which might have, like, let's say, cook some solution.
Yeah, some noise probably.
Yeah. And there you can still tell me something about.
So if you, so in text data you always have some noise. I mean, this assumption is not exactly satisfied, so you will always have some noise. And in that case, also it turns out that you get, reasonable results with this assumption.
Okay, and you will talk about that.
Yeah, later I will talk about it. So again, in the noisy problem, we have this separable structure, and then we add some noise to it. And again, the goal here is to recover the anchor columns. So next I'll talk about the algorithms for near-separable NMF. So let me start with reviewing some recent activity that's been happening in this area. So Esser and co-authors, they came up with this approach where they minimize the Frobenius norm of X minus X transpose H, X times H, and with a sparse penalty on H. So they take the infinity norm of each row of H, and then they take L1 norm of these infinity norms. So this norm penalty induces many exactly 0 rows, and the rows of H that are non-zero, that end up selecting the corresponding columns of X, and they become our anchor columns. So it's, in some sense, it's a sparse regression problem with a row sparsity on H. Now if we have a pure separable problem, in that case it can be shown that this kind of optimization problem can recover all the anchor columns. So we recover all the anchor columns of X by solving this if there are no repeated columns in X. Now there are some drawbacks of this method. So one is that if there are repeated columns or similar columns, then this method will fail. So it will not recover all the anchor columns. Another drawback is that it's not very scalable. So we have to reduce the dimensionality of data and subsample the points to make it scalable. Yeah.
So is that for row sparsity from the H, the shape you draw there, if you want to get the identity on the columns, maybe column sparsity? I was thinking maybe it's column starting makes more sense for H.
So the rows, no, you want row sparsity on H, because row sparsity will give you some non-zero rows in H, right? And those non-zero rows will end up selecting the corresponding column from X. So you can see that here we are multiplying X with H, right? So the rows of H that are non-zero, they will select the column of H, column of X, corresponding column of X. So let's say, let's say there are some rows, so H is a full square matrix now, and there are some rows that are non-zero, right? And here is X. So these rows will select the corresponding columns, and they are now your anchor columns. So again, H is, so there is a subset of rows that are non-zero, and these are your topics. Yeah.
So it seems like the document is tagged one of these topics, these magic topics, these anchor topics, words, but then it cannot, they're mutually exclusive, it cannot be tagged in any other anchor topics. So each of these topics are excluding each other.
Yeah. Yeah. So yeah, I mean, you assume that there is some discrimination in the topics, depending on, I mean, there is at least one word that discriminates them.
No overlap in that sense.
Yeah. So recently, Arora and co-authors, they also came up with the approach where they view this problem as minimizing the Frobenius norm again, but they scale all these points and they solve the convex hull problem. So they recover the vertices of this convex hull, and that gives them the matrix W. But this approach is not very scalable. More recently, Bitorf and co-authors, they propose a linear programming based method where they minimize the Frobenius norm, the norm of x minus x times h under some constraints on h. And this again is guaranteed to recover all the anchor columns if the problem is pure separable. And they optimize it using parallel STD, so the approach is very scalable. And the noise performance is also shown to be better than the Arora paper. Gillis and Vavasis, they also came up with the approach where they view this problem as recovering the vertices of the convex hull, and they use a property that a strongly convex function over a polytope maximizes on a vertex. So they evaluate this function on all the data points, and they pull up the vertices, and they incrementally select the vertices. So in each iteration they select one vertex, and the approach is very fast. The only, I think, one drawback of this approach is that it requires that the set of anchors are linearly independent. So it assumes that the W matrix here is full rank. If it is not full rank, then it will not recover all the anchor columns. So when we started working on this problem, we did some preliminary experiments and we made some observations. So one observation was that real text data is very noisy. So if we take this TDT dataset, it's a classic topic modeling data, and it has 30 topics. So if I take a NMF with 30 inner dimension factorization, in that case the ratio of noise to the ratio of data is about 90%. So 90% of your data is not explained by the separable structure. So it's very important to choose the right noise model. Further, when we are in high dimensions, it can happen that all your columns are anchor columns. So in that case, it's the performance depends on which anchor columns we choose, because there are multiple options and we are only allowed to select only R number of columns. So we have to be selective in choosing the right anchor columns.
Can you tell us a bit about this TDT data set? So like, where did the data come from? How many documents are there?
Yeah, this is topic detection and tracking data. So it was, I think, released in early 2000 or so, and it has 30 topics, and I don't remember the topics exactly, but the number of documents are around 19,000. Yeah.
And the topics overlap, or are they quite distinct?
Topics are fairly distinct. Fairly distinct. Yeah.
How many words? How many unique words?
I think vocabulary size is around 25,000.
R, sorry, what is A? What is
A is the index set of the anchor columns. So the size of so the number of anchor columns actually is 30. So there are 30 topics. Small r, yeah, in the factorization.
And this is by assumption, right? Because the TDT set may not have that property, right?
Yes, I mean it's an assumption that we have in topic modeling. So we are going to test it on this data.
So if you were to run this on TDT and bind R, you will get a different ratio for every R.
That's true. If you increase R, then your then more and more data will be explained by this structure. Yeah, but I mean in the data it's given that there are 30 topics, so they say that 30 topics are there. So there is one more thing about the previous methods, and they work by L1 normalizing the columns of X. So they go after the convex hull problem, and this is problematic in text data, because in text we are more used to using the TF-IDF representation of documents, and we L1 normalize the rows of matrix X. And if on top of it we L1 normalize the columns, then that perturbs the TF-IDF structure. And in our experience, that adversely affects the performance under noise. So these observations, they motivate us to look for something that directly solves the conic hull problem, and there is no need to normalize the columns of X. So again, the approach is a conic hull method to recover the extreme rays of the data cone, and it is inspired by characterization of extreme rays and extreme points from Clarkson and Dula paper. I think this should be 1999. So the approach recovers the extreme rays incrementally, one extreme ray in each iteration, and here I have shown a current cone after 3 iterations. So we have added 3 extreme rays to the cone, and let's say we want to expand this cone by a 4th extreme ray. So to expand this cone, we project all the external points to the cone and find normals to the faces. So you can see the green points are external to the current cone, the blue points are internal to the current cone, and red points are the extreme rays. So we project all the green points to the current cone, and that gives us the normals to the faces of the current cone. Then we take a residual, so we pick a face and then rotate it outside the cone until it hits the last point on that side, and that last point is our extreme ray. So in this case, we add this point as our anchor column, and this is the new extreme ray, and we expand the cone. So here is the algorithmic sketch of the method. So we start with empty anchor set, and we have a matrix R that is initialized to X, and the first step is a selection step where we select the anchor column. So this is done by evaluating this criteria here. So we evaluate R transpose times xi divided by q norm of xi, and xi is the ith column of X, and then we evaluate this vector using the selection operator, and the selection operator takes a vector and gives out a scalar. So we do this for all the columns of X, and the column which gives us the maximum value, that is our anchor column, and we add it to our set of anchors. So the next step is after we have selected this anchor column and we have expanded the cone, in the next step we want to project all the external points to the current cone, and this is done by solving this non-negative least squares problem. So we minimize the Frobenius norm of X minus set of anchors times H with a non-negativity constraint on H, and then we compute the residuals, and every column of the residual is normal to some face of the cone. And now we get the residual matrix, we go back again to the selection step, pull out a new anchor, expand the cone, and then so on. So this is repeated until we have selected the desired number of anchor columns. Now this is really a family of algorithms, because depending on the selection operator here and the q norm, we can have different variants of the algorithm. So one variant is when the selection operator is it takes a vector and the output is the jth element of that vector, and suppose q is equal to 1. So in the denominator we have one norm of xi. So this variant can be shown to solve the pure separable problem exactly. So it recovers all the extreme rays of this data cone, and of course the performance under noise will depend on which element of V is chosen by the selection operator. But if it's pure separable problem, then you choose any element of V and that will solve the problem. Second variant is that selection operator looks like this. So it takes a vector V and takes all the non-negative elements and computes their L2 norm. and q is equal to 2 here. So we take 2 norm of xi. Now this variant is very similar to orthogonal matching pursuit style of algorithms in signal processing, just that it is a non-negative variant of OMP algorithms. And intuitively it picks a column that minimizes the Frobenius norm of the current residual matrix. But this variant does not solve the pure separable problem accurately. So it leaves out 1 or 2 anchors. But this variant actually performs very well under noise. So the noise performance is pretty good.
Sorry,
Yeah.
I have a hard time. What is your measure of success? So did you have so you have this objective which says, oh, so that's the norm of n?
Yeah, we are minimizing the norm of n. So minimize the Frobenius norm of x minus w times h. So that's why we have this Frobenius norm projection here.
And so forth. Do you have like some optimality guarantee? Or? I mean, because you mentioned first if the problem is solvable, I will find it. So we will have norm of n equals 0. Now if I use your algorithm and I get some norm of n, how do I know is it good or?
Yeah, so under noisy problem actually we have shown empirically that it's better than the previous methods, but on the formal guarantees we don't have it yet, so we are working on that. So if it's a noisy problem, then you want to show that if your noise is bounded, then your output of the algorithm is also bounded in some sense. So one advantage of the method is that model selection is very easy because we are incrementally adding these topics. So in every iteration we add one topic. So all the previous solutions, they are contained in the current solution. So we can stop whenever we have some external criteria that is met by the algorithm. And we don't need to rerun it every time for different values of R. And we have a scalable implementation which exploits the row sparsity of matrix H. And both selection and projection step here, they are very easily parallelizable. And as we will see later, it compares favorably with previous methods on the same problem. So let's go back again to this swimmer data. So I've shown here some topics that are recovered by local search methods. So on the left side, you can see it's a bad run for local search because it converts to a bad local optima. And one of the topics here is very heavily corrupted. On the right, I have shown a good run where it converts to a reasonably good local optima. So this is a danger with local search methods, that depending on the initialization, it can converge to a bad local optima.
Can we go back?
Yeah.
So, gosh, is it really that much worse? Do I care?
Here?
Yeah. Like what? Like, I would assume that would, you know, whatever. Let's call that bad one B.
Mm-hmm.
You know, I assume it's never used. Because if you actually use that topic to generate any data, you get a piece of something that doesn't look like any example, right?
Yeah, but again, it has missed one topic because the topic which should have been here, that is not present.
But who tells you how many topics there are?
No, but if you try to reconstruct your data set with these topics,
Yeah.
you will get some factorization error. So it's not an exact factorization.
Okay, so if I threw in a few more topics, what would have happened?
If you throw in more topics, then probably these topics also will be corrupted because because you have more topics, then some of the structure that is present in the current topics, that will move to the next topic.
So it seems incredibly sensitive to something that you couldn't possibly know in practice.
Yes, so in this, I mean, in local search methods, you have to know the number of topics beforehand that you want to recover. So that is like, so that's why, I mean, you have to run for different number of topics.
It's way worse that, like, A doesn't look all that much worse than B. If you told me that if I didn't know the right number of topics, they'd all be screwed up, that's C. Mm-hmm. And I'm like, of course I don't know the number of topics.
Yes.
Tell me the number of
So
topics.
I mean, so that's why people run these methods for different values of small r, and then they basically choose using. Yeah.
But real problems don't have well-defined number of topics.
Yeah, that's true. I mean, any topic modeling
I
method.
guess even the anchor assumption assumes that real data does have that somehow, if you looked carefully enough, the data would tell you that there are this many topics because of the anchor assumption.
Yeah, so with anchor assumption, our method, the advantage is that it incrementally pulls out the anchors. So, I mean, even if you don't know the topics beforehand, you can start running the algorithm and stop whenever you feel that the next topic that you are getting is not does not make sense or something.
I'm sorry, you can go.
I'm just curious. So here I've shown topics by separable methods. So these are the topics recovered by Bitorf method. And Bitorf method has two step size parameters, so primal step size and dual step size. And depending on how you set these parameters, the convergence might vary. So you can see there are some shadows in the topics, and this topic is not very clean. In Gillis and Vavasis, so again the assumption here is that the W matrix should be full rank. So in this data set, it turns out that this assumption does not hold, and that is the reason it stops after recovering 14 topics, whereas there are 17 topics in the data. Now the proposed method, it recovers all the topics, and the topics also look reasonably clean, and there is a clear-cut structure in the topics. Now let's add some noise to this data and see what topics we get using different methods. So on the top left, I've shown topics by local search. So here there is some noise that is crept in the topics, and but rest of them are very clean. In Bitorf, there are some topics that are reasonably well, and in others there is no clear-cut structure. In Gillis and Vavasis, it turns out that almost all the topics are kind of blurry, and there is no structure in the topics. In the proposed method, there are some topics that are not very clean, like this one and this one, but the rest of them are kind of reasonable, and there is no noise that is crept in the topics. So here is an experiment that tests this method on recovery of anchors. So the generative model is that we generate X by W times H plus some noise, and W is uniformly generated between 0 and 1. H has a separable structure, so the first 20 columns of H are identity, and the rest of the columns are sampled from a Dirichlet distribution, so they lie on the simplex.
The streamer data is not, it's synthetic as well, right? It's a truly,
Streamer is synthetic data, yeah. But it satisfies the separability assumption.
Okay.
Yeah.
It's an odd choice of synthetic data. It's more like image, it's more like vision you're doing, document. You're finding basis functions for these swimmers.
Yeah, right. But the data has an exact factorization, and if you look at the right factor matrix, you will have the columns of identity there. So basically, this data satisfies the separability assumption.
You have more document-like data, toy data that you try to.
Not really. So yeah, in this one we have a pure separable structure, and then we add some noise, and the noise is a Gaussian noise with zero mean and delta standard deviation. So here is the result. So on the x-axis we have the noise level, which is the standard deviation of this Gaussian distribution delta, and on the y-axis I have the fraction of anchors that are correctly recovered by these methods. So the black curve here is the proposed X-ray method. The red line is the hot topics, which is the method of Bitorf, and their name is as hot topics. And the blue line here is by Gillis and Vavasis. So in this type of noise, it turns out that X-ray is better in recovering the anchor columns exactly under noise. And of course, as we keep on increasing the noise, the performance drops. Now in this experiment, we want to evaluate the selected features or selected words on a prediction task. So again, every row of X is a data point, is a document, and we are selecting columns. That means we are selecting words from this corpus, and then we train a multi-class SVM using these selected words, and we want to evaluate the prediction accuracy using these anchor words. So we use two datasets, TDT and Reuters. TDT has 30 classes, 30 topics, and Reuters has 10 topics. Now on the x-axis I have the number of selected words, anchor columns. On the y-axis I have the SVM accuracy. So you can see that as we keep increasing the number of words, the accuracy increases uniformly. But there is a huge gap between the proposed X-ray method and Bitorf and Gillis. So the magenta line is the X-ray greedy variant, and the black line is the provably correct variant of X-ray. So both these variants are better than the previous methods.
Is the local search just the greedy local search on this chart? I don't know.
Local search is not there, but it lies somewhere. So it's better than the separable methods. It lies somewhere here, I think. Somewhere here. And the reason is that because it's not restricted to selecting only the columns, because it allows mixing of these columns, right? So you get better prediction accuracy.
Okay.
Yes.
Sorry, I'm lost. I don't understand this graph. So you have a classification experiment.
Yeah.
And so you use the lower dimensional representation.
So we use matrix W to train our classifier.
Okay. And number of selected features is R.
Is the number of columns in W? Yeah, R.
But is it that you shrink a bigger R, or is it that you solve the problem for a given R and fit it to the SVM?
On the x-axis I have the number of selected features, so number of columns in W, and as you keep increasing the columns, your accuracy keeps going up, because you add more and more features to your classifier, and you want to see how good are these features on a prediction task. So you want to evaluate the quality of these selected features.
What is the performance you get with the original word?
With what?
Yeah.
That's the dotted black line. If you use all the words.
Some other dimensionality reduction technique like SVD, I don't know, how would that look?
So we evaluated non-convex NMF methods, and they are little bit better than separable methods in terms of prediction performance. SVD I did not try, I think.
Because that would be a natural thing.
So the obvious question is, why not just use SVM for all the features? These are linear SVM, right? So I guess the answer is, does this scale better to a larger data set? But then you have to identify all these topics. If you've got 100 million documents or a million documents, it's a big problem identifying the topic. So why not just use linear SVM?
Yes, I think you are right in that sense, because pulling out these anchor columns takes time. And I think linear SVM will be faster if you use just all the words. But this experiment was just to evaluate the quality of words that are selected by these different methods and test their prediction performance.
Do you use all the data for the factorization and then only the training set for the training?
So we split data. So the number of documents we split in 20 and 80. 20% is for training and 80% is for testing.
So you use the same training set for both the SVM and learning the H matrix? Or you learn the H matrix on the whole data set?
It's on the whole data. So it's totally unsupervised. So it's on the whole data.
Is there a point? So basically, like most papers which deal with those dimensionality reduction, they show that at one point, if the training set is small enough, the representation you get by doing the decomposition is better. Did you look at this? Like so I can. So you say I have 20% training. Now let's say I go to 4% training. Is it better than the original features or not? Most papers try to sell it in this way. I don't know if it's the right way to sell it, but that's
that
most common curve we see, right?
That makes sense. Yeah.
My unsupervised algorithm allow to make up for the lack of training.
For the lack of training data, yeah, I think that makes sense. But I think in this experiment we didn't try it. I think I increased started from 20%, then increased it further, and I observed that it's not better than if you use all the words. But maybe if we have like 10% or 5% training data, then I guess these methods will outperform probably. So this experiment evaluates the selected features on clustering task. So I mean, I'll not go into more detail here, but you can see the magenta curve and the black curve are the proposed methods. So they are better than Bitorf and GLS on both these data sets. Here are some large scale experiments that we did. So we evaluate it on 3 data sets, RCV1, PPL2 and IBM Twitter data. And the statistics of the data sets are here. And we compare with hot topics, which is the method by Bitorf and co-authors. So this is also a very scalable method, and it's optimized using STD. And you can see that on PPL2 we are about 3 times faster than hot topics, and on Twitter data, which is very very sparse, we are around 60 times faster than hot topics. So we have a scalable algorithm that can be practical.
And you get a lower error.
So we didn't look at the factorization error here. Yeah. So it's just the running time for recovering 100 topics.
But if you don't set the error, I mean, I can give you a solution very fast.
So the problem is that if you compare the error, it's not apple to apple comparison, because in hot topics you optimize a different norm on the error, and in X.
I mean, let's say you put yourself in a favorable condition and measure the Frobenius norm of n, right?
Yeah.
And then look at it and
yeah, I mean, I'm sure that if you look at the Frobenius norm of noise, then X-ray will be better, because hot topics you optimize some different norm. So, yeah. So next I'll move on to some extensions of these algorithms to other loss functions like L1 loss and Bregman divergence. So let me start with introducing the problem of low rank approximation. So in low rank approximation, we are given a matrix X, and we want to approximate it with a low rank matrix L. And so in the objective we have a rank penalty here, or we have a rank constraint. And this problem is non-convex, but we can get a global solution using SVD in polynomial time. Now we can imagine a robust counterpart of this problem where we assume that the noise matrix is sparse. So we replace the Frobenius norm by L1 norm and we retain the rank constraint as it is. So this problem is also non-convex, and it is also believed to be NP hard. So both these earlier problems that I discussed, we can imagine a non-negative rank version of these problems. So in non-negative low rank approximation, we are given a non-negative matrix X, and the goal is to approximate it with a non-negative matrix L with this constraint that non-negative rank of L should be small. And this problem is exactly the NMF problem, which is NP hard. Now in the robust version of this problem, we assume that the noise is sparse. So we replace Frobenius norm by this L1 norm, and we have the non-negative rank constraint. And this problem is also NP hard. Now both these approximations, the low rank approximation and low non-negative rank approximation, they can be used to do foreground-background separation. So background is something which is slowly varying across data points, and foreground is something which is varying relatively faster, but it has low energy. So it can be used to do foreground-background separation in video as well as in text. But because the previous versions of the problems are NP hard, the question is how to make them tractable. So here is one popular approach to make robust low rank approximation tractable. So they replace the rank function by this nuclear norm penalty, and then this problem becomes convex. And this is well studied in the literature under the name of robust PCA. In the robust low non-negative rank approximation, we propose to use separability assumption to make it tractable, because this problem earlier which we saw, this was NP hard. So we propose to use separability to make it tractable. So the problem is that we want to minimize the L1 norm of X minus W times H with a separable structure on H. And the question that we ask is how does it compare with convexified robust PCA on common applications? Now before going into this, I'll talk about the algorithm that we have. So again, this is a conical algorithm that recovers the extreme rays of the conical hull. And this time we do it with the L1 residuals. So we project all the external points to the current cone, and the projections are in terms of L1 norm. And once we have these projections, we pull out a new extreme ray using these L1 residuals and expand our cone. So here is a sketch of the algorithm. We start with empty anchor set and the matrix D is initialized to X. So the first step is the selection step, where we evaluate this criteria here, and that gives us the next anchor column. So Di is the ith column of D, Xj is the jth column of X, and P is any positive vector. So whichever column of X gives us the maximum value of this criteria, that is selected as the anchor column. And once we have expanded the current cone, we take our external points and then project onto the current cone. And this is done by solving a non-negative least absolute deviation problem. So we minimize the L1 norm of X minus set of anchors times H with a non-negativity constraint on H. And the matrix D is just the matrix of subgradient of this loss function. So if the residual entry is 0, we have Dij as 0. If the residual is non-zero, then we have the sign of the residual as Dij. And once we have the matrix D, we go back to the selection step, pull out a new anchor and expand the cone. And this is done until we have the desired number of anchors. Now this procedure, it can be shown that it probably solves the pure separable problem. But again, in the noisy version, it will depend on which I we end up choosing here. Now, this method can also be extended to handle more general loss functions like Bregman divergence. So I want you to focus on the last bullet here. So we want to minimize the divergence between X and W times H, and we have a separable constraint on H. And so this problem, we have a selection criteria that recovers the anchor columns using Bregman divergence, but I'll not go into more detail here because I don't think we have enough time. So this is again to test the method on recovery of anchors. So generative model is X equal to W times H plus noise, and W is again uniform between 0 and 1, H is separable, and the noise matrix is now Laplace. So it's sampled from a Laplace distribution with 0 mean and delta standard deviation. And once we have the noise, we make all the negative entries equal to 0. So there are approximately 50% entries in the noise that are 0. And the recovery performance is here. So on the x-axis, I have the standard deviation of the noise, which is delta. On y-axis, I have the fraction of anchors that are correctly recovered. So the black curve is the proposed robust X-ray method, and it's better than the previous methods. And this experiment is just as a sanity check to make sure that the method is performing as expected. So it performs well under the sparse noise setting. Now let's go back to the foreground-background separation problem in video. So again, here our data matrix is such that we have each row a video frame, and we want to decompose it into two matrices, a low non-negative rank matrix and a sparse matrix. So low non-negative rank matrix will model the background, and sparse matrix will model the foreground. And we want to see how separable NMF methods perform under this setting. So here I've shown some images on this data. So you can see that the separable method with the inner dimension of 2, it recovers the background and foreground reasonably well.
Sorry, I have a hard time seeing the intuition for using a non-negative decomposition for image data. It means that you cannot lower the intensity when you have those components, which for text, I guess it's more intuitive than for intensities.
So you are asking in terms of separable methods or in general NMF?
In general, why would I use a like I have pixel intensities and I want to have like a kind of decomposition, and I'm only allowed to add them up. It seems that you might want to subtract things, or
yes. So I mean, the most popular methods for this problem are, as you said, based on robust PCA, where you allow negative entries. Our motivation was to check whether non-negative matrix factorization does perform well for this problem or not. And again, I think the intuition is that so your background is a low non-negative rank matrix, and I guess you want to represent every pixel that is present in the video frame as a non-negative combination of certain elements. So again, like text data, this is also a non-negative data. So I mean, the motivation.
Having high intensity because of one of the topic, and then maybe you want to subtract it if another topic is present. Let's say a topic is something hiding a lamp or something, right?
Mm-hmm.
I cannot do that, right? And for text data, it's kind of intuitive that you don't put a topic and suddenly delete words.
Mm-hmm.
For images, it seems counterintuitive to me, at least. I don't know.
I mean, you can also look at it in terms of in a geometric sense. So if you take all the pixels, right, and you represent it in a space, so all your data is contained in the non-negative orthent, and all you are doing it to basically bound this data in a cone, basically. And I mean, that can always be done. And now you are asking whether there exists a cone with very small number of extreme rays that can basically model the background.
The data example is valid, right? I mean, if you have a corpus where there's several light sources and the light sources just are on or off,
Mm-hmm.
where it would make sense to have specific just topics corresponding to the lighting being on or off in certain ways, which would just illuminate certain fraction of pixels, right?
But again, if some pixels are off, for example, you can put a low weight on the off light source.
Each of them would be just a positive factor, and they would be on or off. They would be present or absent, but not be negative.
No, I mean, they can be any real number bigger than 0. Yeah.
Filter. You probably could combine. Like a filter would be an example.
That seems kind of like if you give me like scans, ink stuff, I totally buy it. If you give me like natural images, I can see both effects in terms of explaining the image like with a few source of variation.
Mm-hmm.
I can see that you have subtracting effect in the same topic as additive effect.
Mm-hmm.
Let's say you have something moving in front of a light source, right?
Right.
So it would basically let's say this thing is left or right? So this exactly. So you would need like 4 topics there instead of 2 because you cannot subtract anything.
Yeah, I mean, that's always there. So you may end up increasing your number of topics if you have this non-negative constraint. But again, on this data, actually, this result was obtained with the factorization of inner dimension 2. So it's a very low rank factorization.
Did you compare with SVD, PCA?
Yeah, I have it in the next slide. So this is a quantitative comparison between robust PCA and separable NMF. So again, in robust PCA, we don't have any non-negativity constraints on the low rank part. So we use 2 data sets here, Bootstrap and Airport Hall. And for these 2 video data sets, we have the correct ground truth. So we know which pixels are foreground. So we have them labeled. And here I've shown the ROC curves for these 2 data sets. So on the x-axis, I have the false positives. On y-axis, I have the true positives. So in these 2 data sets, you can see that robust X-ray is as good as robust PCA, is performing as good as robust PCA. And the advantage that we get here is of speed, because in robust PCA, you have to solve, in each iteration, you have to solve a SVD problem. So this in some sense limits the speed.
What is the result of like a pure SVD, like in general it works well. Like the first thing I would try is that you give me a bunch of images, right? We do SVD and subtract the main components as the foreground.
Yes, yeah. So,
and that would mean I solve the problem once, right? The SVD problem.
Right. So robust PCA is just a convex relaxation of the SVD problem, because I mean in SVD you have to know what rank you want, and here you have.
So what I'm saying is that you're saying two things. There's a low rank representation which explains the background, and there's this sparse foreground, right?
Yeah.
Let's say I remove the sparse foreground.
So you assume that
I plot the rock curve. So the problem becomes very simple to solve. And maybe I get most of the performance, right? We don't know that.
So in SVD the assumption is that you have Gaussian noise. Right?
Yeah, no, I agree that I'm not fully using all the assumption I could use to solve the problem.
But again, I mean, I think in this sort of setting where foreground-background separation, I think SVD is not going to perform well. So you need to model the sparsity of foreground. Now this is my last application here. So so far we saw that we had data points along the rows of this matrix, and we were selecting columns. So this was equivalent to selecting some features from the matrix. And now let's say we transpose this matrix X. So in this case we'll select some samples from the data which are representative or exemplars of your whole data sets. So this setting can be used in video summarization or in text corpus summarization in terms of a few documents or a few number of frames. And we compare, in this setting we compare our method with this method which was proposed in 2012, and they do it by solving this problem. So they minimize the Frobenius norm of x minus x times c, and there was row sparse penalty on c here. And these are the results. So we use Reuters and BBC, which are text data sets, and the setting here is that we select some samples and then we train a SVM with those selected samples, and the hope is that if the selected samples are diverse enough, in that case we can get a good prediction error with a small number of samples. So on the x-axis I have the number of selected samples, and on the y-axis is the prediction accuracy. So as we keep increasing the number of samples, we get a jump in the prediction accuracy, and the red line and the black line are the X-ray method, and the magenta line is the method by Alhamifar. So on Reuters, I think robust X-ray is better than both these methods, and on BBC it turns out that Frobenius norm version of X-ray is better than the robust version and Alhamifar. So in the end, I'll just summarize what we discussed. So we saw the separability assumption, and it makes the NMF problem tractable, and it turns out to be a reasonable assumption in topic modeling and hyperspectral unmixing. We also saw a scalable family of algorithms for near-separable NMF, and the algorithms are based on recovering the extreme rays of the conical hull, and they directly attack the conical hull problem, and it is not required to scale the columns of X. And the solution is built up incrementally, so we select one extreme ray in each iteration, so it's very easy to do cross validation. We also outperform the previous methods in terms of performance and speed, and the algorithms can be extended to other loss functions like L1 loss and Bregman divergence. Now in the future we want to do a formal noise analysis of the method, and we also want to work on the streaming version of the algorithms where either rows or columns of X are coming in a streaming fashion. In the end, I'll acknowledge my collaborators here. So Vikas, Sindhwani and Prabhanjan Kambadur from IBM TJ Watson. And I'll just very briefly mention some other work that I have done. So I worked on multitask learning, modeling the grouping structure in multitask learning. I have also worked on multiple output regression where we model the conditional mean and conditional inverse covariance structure on the parameters. And I've also worked on a little bit on transfer learning. In this line of work, I have worked on multiple kernel learning. So we are given a set of kernels and we want to combine those to learn a final good kernel. Here, the setting is that we are given multiple similarity graphs and we want to learn spectral embedding combining these similarity graphs. So both these approaches, they are based on either co-training or co-regularization. And this problem setting is that we have a database in which we have data points from one modality and the query is coming from a different modality. And the goal is to, given a query, we want to recover the corresponding element from the database. So one example is like image retrieval from text query and vice versa. And I guess that's it from me. And thank you very much for your patience. Thank you.
Any last 10 questions?